Next, we are going to talk about the transformer, which will be used in homework 5. We have already mentioned the transformer many times. If you still don't know what a transformer is, the transformer here is different from the transformer that Optimus Prime is. The transformer is strongly related to Bert. So, here is a Bert poking out his head to demonstrate that transformer is strongly related to Bert. What is a transformer? A transformer is a sequence-to-sequence model. We denote sequence-to-sequence as SEQ to SEQ. Then, what is a sequence-to-sequence model? When we talk about inputting a sequence, when the input is a sequence, there are several possibilities for the output. One is that the input and the output have the same length, which is the case in homework 2. Another case is that the output is an item, which is the case in homework 4. The case of homework 5 is we don't know how long the output will be. The length of the output is determined by the machine itself. In what circumstances or applications will we need to use the sequence-to-sequence model? That is, the input is a sequence, and the output is a sequence, and we don't know the length of the output. The output length should be decided by the machine. What kind of applications are there? For example, a good application is speech recognition. When doing speech recognition, the input is a sound signal. We have seen this in our course many times. The input audio signal is a sequence of vectors. What is the output? The output is the result of speech recognition, which is the text corresponding to the input audio signal. We use circles to represent text. Each circle represents a word in Chinese. Of course, the length of input and output have some sort of relationship, but there is no absolute relationship. We say that the input audio signal has a length of big T. We have no way of knowing what is the exact length n. According to the input length T, it is up to the machine to decide how many texts it should output. By listening to the content of the audio signal, the machine should decide how many words the output sentence should contain. In the speech recognition result. This example is speech recognition. There are many other examples. For example, in homework 5, we will do machine translation. The machine read sentences in a language and output sentences in another language. In a translation task, the length of the input text n doesn't necessarily correspond with the length of the output n prime. The model decides the relationship between n and n prime by itself. If we give the machine the phrase machine learning in Chinese, the output is machine learning in English. There are 2 English words in the output and 4 Chinese words in the input. But obviously, you can't simply divide the length of any Chinese sentence by 2 to obtain its English translation's length. So given any input, the machine should find out the length of the output text by itself. With this technique, we can handle even harder problems. For example, speech translation. What is speech translation? In this problem, a person says some words. For example, machine learning. Then, the machine doesn't output the English words. It outputs the Chinese translation of the sentence directly. In the previous example, the input is the audio machine learning, and the output is machine learning in Chinese. Some of you might be asking, why we need to do speech translation? Why don't we put a speech recognition model and a language translation model together to handle this task? Obviously, combining these 2 models gives a speech translation model. But the problem is, most languages in the world don't have characters. There are more than 7,000 languages in the world, but more than half of those languages don't have characters. For these languages, we can't separate the translation task into 2 tasks. Since there are no characters to represent the sentence, the first part would fail. So is it possible that we don't separate the task into 2 parts, but directly translate the audio into a language that can be written down? Taiwanese Hokkien is a good example of such language. Taiwanese isn't a language that don't have characters at all, though. Many people think that Taiwanese can be written down, but those characters aren't that popular. I've heard that elementary schools nowadays teach Taiwanese Hokkien characters, but most Taiwanese Hokkien users still can't understand those characters. Suppose you are using a Taiwanese Hokkien speech recognition tool. You might fail to understand the output text, since you don't know the words. Right? That's why we seek for a machine that is able to do translations. We want a machine that receives a Taiwanese Hokkien sentence and outputs a Chinese sentence with exactly the same meaning, so that ordinary people can understand it. Is it possible to do this? Is it possible to train a neural network that receives audios of a certain language and outputs texts with the same meaning in another language? The answer is yes. In general, to train a neural network, we need to find relationships between inputs and outputs. Suppose we want to train a Taiwanese Hokkien speech translation model. Then, we need some known correspondence between Taiwanese Hokkien audio and Chinese characters. But is it easy to collect such information? Well, sometimes it is still possible. For example, there are many Taiwanese soap operas on YouTube. These Taiwanese soap operas have Taiwanese audio and Chinese subtitles. So, if we download those Taiwanese audio and Chinese subtitles, we can acquire a dataset that has corresponding audio and words. With that data, we can train a model. In theory, we can use a transformer, which we will introduce later, to train a Taiwanese speech recognition model that takes Taiwanese audio as input and outputs Chinese subtitles. You might think this idea is infeasible and comes with many difficulties. Well, our lab downloaded 1,500 hours of Taiwanese soap operas and actually trained a speech recognition system. You might think that there are a lot of potential problems. For example, there could be a lot of noises, such as background music. Let's ignore that for now. Moreover, the subtitles might not necessarily match the audio. Let's also ignore that for now. You might also wonder if we can first Romanize the Taiwanese audio and convert it into phrases written in English characters with similar pronunciations. Maybe we can use these phrases as an intermediate and then convert these phrases into Chinese. Well, we trained the model directly. Without overthinking too much, we take the Taiwanese audio as input and output the Chinese subtitle. Without thinking too much, we gave it a try. You might wonder if such reckless training can actually work out and train a speech recognition system successfully. In fact, it is actually possible. Here are some actual results. After training on 1,500 hour-long Taiwanese soap opera audio, the model can take Taiwanese audio as input and successfully output Chinese subtitles. Let me show you some sample inputs. You can try to translate it yourself and see if your translation is the same as the model. This is what the model heard. Your body can't hold it. Taiwanese. What is the output of the model? The output is, your body can't hold it. This audio means, your body can't hold it, in Taiwanese. The machine translated it into a Chinese sentence instead of a Taiwanese sentence. Let's try another example. This is what the model heard. Why did you ask for leave if you're fine? Taiwanese. The sentence is, why did you ask for leave if you're fine? When the model heard the word, fine, it output the word, fine, in Chinese instead of Taiwanese. The Taiwanese word for fine has 4 syllables, which is the same as what the model heard in the audio. However, the model correctly translated the audio into the Chinese word for fine, which only has 2 syllables. Despite all that, machines still often make mistakes. And here is an example of it. I'll show you the clip, and you can have a listen. Aren't you tired of it? Taiwanese. It means, aren't you tired of it, in Taiwanese. When I heard it myself, I thought my answer would be the same as the machine, which is, are you about to give birth? But, in fact, this sentence means that, won't you get tired of it? Won't you get tired of it? Of course, the machine inverts it. You know that, sometimes, from Taiwanese Hokkien to Chinese, you need to invert the sentence. It doesn't learn well in the inverting part. For example, it hears the sentence like this. I asked the factory manager for help. He said, I asked the factory manager for help. The output of the machine is, I helped the factory manager ask something. But, you know that it is actually an inverted sentence. I asked the factory manager for help is me to ask the factory manager for help. But, for the machine, If the relation between Taiwanese Hokkien and Chinese needs to be inverted, it seems to be a little difficult to learn. This example wants to tell you. Direct conversion from Taiwanese Hokkien voice signal to traditional Chinese is not impossible. It is possible to achieve. In fact, many people in Taiwan are doing speech recognition of Taiwanese Hokkien. If you want to know more about speech recognition of Taiwanese Hokkien, you could take a look at the website below. The reverse of speech recognition of Taiwanese Hokkien is speech synthesis of Taiwanese Hokkien, right? If the model's input is Taiwanese Hokkien voice, and its output is Chinese text, that is speech recognition. In contrast, if the model's input is text, its output is voice signal, that is speech synthesis. Here, we are going to demonstrate the speech synthesis of Taiwanese Hokkien. The data used here is Taiwanese Hokkien voice dataset. You could search from Google Taiwanese Hokkien voice to get this dataset. Inside, it is the voice signal of Taiwanese Hokkien. It sounds like this. For example, you tell it that, "Welcome to the Speech Processing Laboratory of National Taiwan University." Just for clarifying here, there is no real end-to-end model yet. So, the model here is still divided into two stages. It will first convert the Chinese text to Tai Luo pinyin of Taiwanese Hokkien. It's like the KK phonetic transcription of Taiwanese Hokkien. Second, it will convert the KK phonetic symbols of Taiwanese Hokkien into sound signals. However, from the KK phonetic symbols of Taiwanese Hokkien to sound signals, it is a network-like transformer. It's actually a model called Ecotron, which is a sequence-to-sequence model. It looks like this. So, the text you input is, "Welcome to Speech Processing Laboratory of National Taiwan University." The output of the machine is, "Welcome to Speech Processing Laboratory of National Taiwan University." Or, you say this Chinese sentence to it. Then, the Taiwanese Hokkien it output is, "Pneumonia is really serious recently. And you should remember to wear a mask and wash your hands frequently. And you should go to see a doctor if you are sick." So, you really can synthesize the voice signal of Taiwanese Hokkien by what we have learned from this course. For example, transformer or sequence-to-sequence model. What I just said is much related to speech sounds. In text, the sequence-to-sequence model is also widely used. For example, you can use the sequence-to-sequence model to train a chatbot. A chatbot is a machine. When you input a sentence, it will give you a response. Both the input and the output are all texts. Text is a vector sequence. So, you can use the sequence-to-sequence model to make a chatbot. How to train a chatbot? You have to collect a large number of human conversations. You can collect conversations like TV series, movie lines, and so on. You can collect a bunch of conversations between people. Suppose in the dialogue, there is someone who said, "Hi," and another person said, "Hello, how are you today?" Then you can teach the machine that when the input is, "Hi," the output should as close to, "Hello, how are you today?" as possible. Then, you can train a sequence-to-sequence model. Say something to it, and it will give you a response. The usage of the sequence-to-sequence model in the field of NLP, or in the field of natural language processing, is more extensive than you think. Many natural language processing tasks can be thought of as question answering. That is, QA tasks. How? The so-called question answering is when the machine reads a piece of text. You ask the machine a question, hoping that it can give you a correct answer. A lot of tasks that you think are far away from question answering can be considered as QA. For example, suppose what you want to do is translation. The article comes out to be an English sentence. What is the question? The question is, what is the German translation of this sentence? Then machine outputs the German answer. Or you want the machine to summarize automatically. The summary task is machine reads a long article, and the machine extracts the key points of this article. That is, you just have to give the machine a piece of text. And the question is, what is the summary of this text? Then expect it to output a summary. Or you want to ask the machine to do sentiment analysis. What is sentiment analysis? That is, the machine has to judge a sentence automatically. is positive or negative. The application is like, suppose you have made a product. You want to know the opinion of netizens. But it's impossible that you always find someone on the PTT to read every article. Then what to do? You train a sentiment analysis model. You saw an article mentioning your product. Then you feed this article into your model to judge this article is positive or negative. How to view the sentiment analysis problem? As QA problems? You can give the machine the article you want to judge. Then your question is the article positive or negative? Then I hope the machine can tell you the answer. Thus, a wide variety of NLP problems can often be regarded as QA problems. And the QA problem can be solved by the sequence-to-sequence model. But how to use the sequence-to-sequence model to solve the QA problem? There is a sequence-to-sequence model. Input is the concatenation of the article and the problem. And the output is the answer. It's over. The concatenation of your question and article is a very long text. And its answer is a paragraph of text. As long as the input of the sequence-to-sequence model is a paragraph of text, the output is a paragraph of text. That is, input a sequence and get a sequence as the output to solve the problem. So, you can solve QA questions by using the sequence-to-sequence model. Let it read an article and a question, and just output the answer directly. So, all kinds of NLP tasks have the opportunity to use the sequence-to-sequence model. But I must emphasize here that you will often get better results for most NLP tasks or most speech-related tasks if you customize the models for these tasks. Solving different problems by sequence-to-sequence model will be just like doing everything by Swiss knives, right? Swiss knives can do all kinds of problems. You can use a Swiss knife to chop wood. You can also use a Swiss knife to cut vegetables. But it's not necessarily the best one to use. So, if you customize various models for different tasks, you often can get better results than just using the sequence-to-sequence model. But the customized model for each task is not the focus of our course. Suppose you deal with human language, including speech or natural language processing, and you are interested in these related tasks. In that case, you can refer to the link for the course webpage below. It is the course of Deep Learning and Human Language Processing last year. This course's content will teach you what the best model for all kinds of tasks should be. For example, doing speech recognition. What we just talked about is a sequence-to-sequence model. Input a sound signal and output text directly. Today, Google's Pixel 4 also used end-to-end neural network, which is officially supported by Google. What is inside Pixel 4 is a neural network. Input audio signal and get the text as the output. But it is not using the sequence-to-sequence model. It used a model called RNN transducer. These models are designed by certain characteristics of speech. It can perform better. As for what kind of customized model should be for each task, it is the subject of another course. It is not the focus of our discussion today. I just talked about many sequence-to-sequence models with their applications in speech and natural language processing. There are still many applications that it does not look like a problem that can be solved with the sequence-to-sequence model. But you still can use the sequence-to-sequence model to solve the problem. Take grammar analysis as an example. What grammar analysis needs to do is, given a paragraph of text, such as deep learning is very powerful, the machine has to produce a grammatical analysis tree. The tree can tell us that the combination of deep and learning is a noun phrase. The combination of very and powerful is an adjective phrase. The combination of the adjective phrase and is a verb phrase. The combination of the verb phrase and noun phrase is a sentence. What we do in grammar analysis is to parse a syntactic tree like this. Suppose you want a deep learning solution. In the task of grammar analysis, input is a piece of text, which can be seen as a sequence. But the output does not look like a sequence. The output is a tree structure. But in fact, a tree structure can also be thought of as a sequence. Why? This tree structure can correspond to a sequence like this. From this sequence, you can also see an opening parenthesis. and a closing parenthesis. In this tree structure, there is a noun phrase in S and there are also opening parenthesis and closing parenthesis. There are opening parenthesis and closing parenthesis in VP. We can also see is in VP. Then there is an adjective phrase and there are also opening parenthesis and closing parenthesis. This sequence represents the structure of this tree. After you convert the tree structure into a sequence, you can use the sequence-to-sequence model to solve it. You can train a sequence-to-sequence model. The input is this sentence. The output is this piece of text. We can convert this piece of text into a tree structure. So that's how to use the sequence-to-sequence model to do grammar analysis. This idea sounds very crazy. But the network is trainable. You can read a paper called Grammar as a Foreign Language. This paper is not too new. You can see that its uploaded time on arXiv is the end of 2014. So it's an ancient paper. When this article came out, the sequence-to-sequence model was not popular then. At that time, the sequence-to-sequence model was mainly used in machine translation. So the title of this paper is called Grammar as a Foreign Language. He regarded grammar analysis as a kind of machine translation. He viewed grammar as another language and applied the sequence-to-sequence model. That was thought to only be used for translation. As a result, he got the state-of-the-art result. I have met the first author Oriol Volnials at an international conference. At that time, the sequence-to-sequence model was still a very trendy thing. From my point of view, I thought this model could be pretty hard to train. I asked him, were there any tips to train a sequence-to-sequence model? I didn't expect you used a sequence-to-sequence model to do grammar analysis and reach the state-of-the-art result. There should be some great tips. However, he said that there were no tips. He said I didn't even use Atom. I directly used gradient descent to complete the training. The training was successful on my first try, but I adjusted the hyperparameters a little bit to reach the state-of-the-art result. I don't know whether what he said is real or fake, but these days, the sequence-to-sequence model has been widely used in all kinds of applications. There are also some tasks that can be done using sequence-to-sequence models. For example, the classification of multi-label. What is the classification of multi-label? You have to compare multi-class classification with multi-label classification. Multi-class classification and multi-label classification sound like the same, but they are actually different things. Multi-class classification means we have more than one class and the machine has to select a certain class from several classes. But multi-label classification means that a single object can belong to more than one class. For example, when you are doing article classification, maybe this article belongs to classes 1 and 3. This article belongs to class 3, 9, 1, 7 and so on. You might wonder how to solve this kind of multi-label classification problem. Can we just treat it as a multi-class classification problem? For example, I threw these articles into a classifier. Originally, the classifier would only output one answer. The answer with the highest output score. I will now take the top 3 with the highest scores and see if they can solve the multi-label classification problem. But this method may not work. Why? Because the number of classes corresponding to each article is not the same at all. Some articles correspond to 2 classes. Some are 1 and some are 3. So if you say I just set a threshold and directly select the top 3 highest scores, the top 3 with the highest classifier output score, as my output, we cannot get good results obviously. You can use sequence-to-sequence to do it brutally. The input is an article and the output is class. That's it. The machine decides how many classes it should output. We say that sequence-to-sequence model is to let the machine decide the numbers of output and the length of the output sequence. Since you have no way to determine the number of classes, the machine helps you decide. It decides on its own the number of classes each article belongs to. Take object detection as another example. This looks far from the sequence-to-sequence model. It can also be brutally solved by a sequence-to-sequence model. Object detection is that given the machine a picture, it frames out the objects in the picture. Also, it recognizes this as a zebra and this also as a zebra. But this kind of problem can be done with sequence-to-sequence brutally. As for how to do it, we won't go into details here. I will put a link for your reference. All I wanted to tell you is that sequence-to-sequence model is a very powerful model. It is a very useful model. We are going to learn sequence-to-sequence models. Generally, sequence-to-sequence model is divided into two pieces. One is the encoder, and the other is the decoder. After you enter a sequence, the encoder is responsible for processing this sequence, and then throws the processed result to the decoder. The decoder will determine what kind of sequence it should output. We will talk more about the internal architecture of encoder and decoder later. The origin of sequence-to-sequence model, in fact, was very early in September 2014. There is an article using sequence-to-sequence model for translation on arXiv. You can imagine the sequence-to-sequence model at the time looks pretty naive. Today, when we talk about sequence-to-sequence model, the first thing that comes to everyone's mind is our topic today, which is the transformer. It has an encoder and also a decoder. There are multiple submodules in it. We'll talk about what is the function of each submodule. Okay, let's talk about the encoder. What the encoder of a sequence-to-sequence model does is to generate a sequence of vectors from the input sequence. Generating a sequence of vectors from another sequence of vectors can be done by many other models. Maybe the first thing that comes to everyone's mind is self-attention, which we just talked about. In fact, not only self-attention, but also RNN or CNN can actually do it. Input a sequence of vectors, and then output another sequence of vectors with the same length. Inside the transformer, the encoder of the transformer uses exactly the self-attention. It looks a little bit complicated here. Let's use another picture to explain the architecture of the encoder clearly, and then compare to the graph in the original paper of transformer. In this encoder, there are many blocks. Each block will get a sequence of vectors as the input, and then output another sequence of vectors. You input the first block a sequence of vectors and the first block outputs another sequence of vectors. This sequence of vectors is also inputted into another block. The last block will output the final vector sequence. Each block is actually not a layer of the neural network. The reason that we don't call each block a layer is that the things being done in each block are actually done by several layers. In the encoder of the transformer, what each block does is like this. First, do the self-attention. After inputting a sequence of vectors, it performs the self-attention. It considers the information of the entire sequence and outputs another sequence of vectors. The output vectors will pass through a fully connected feed-forward network, and another sequence of vectors will be outputted. This sequence of vectors is the output of the block. In fact, in the real transformer, what it does is more complicated. What it actually does is like this. This is a layer of self-attention. When we talked about self-attention, we said that after we inputted a sequence of vectors, another sequence of vectors would be outputted. Every vector here is the result after considering all the input. In the transformer, it has a special design. We don't output this vector only. We also add its input to itself. It adds the input directly to the output and gets the new output. Here, suppose this vector is called A, and this vector is called B. You will add up A and B, and treat it as a new output. Such a network architecture is called residual connection. In fact, residual connections are widely used in the field of deep learning. If we have time later, we can discuss more of it in detail. Why use residual connection? For now, you just have to know that there is a type of connection, a type of network design architecture called residual connection. It will sum the input and the output and create a new vector. After getting the residual result, we do another thing called normalization. What we do here is not batch normalization. Rather, it is called layer normalization. What layer normalization does is a little simpler than batch normalization. What layer normalization does is like this. Input a vector and output another vector. There's no need to consider batch here. When we were talking about batch normalization, we need to consider batch. However, layer normalization does not need to consider batch. It inputs a vector and outputs another vector. So, what exactly does layer normalization do? It will take the input vector and calculate its mean and standard deviation. But pay attention here. When doing batch normalization, we are calculating the mean and the standard deviation of different features in the same dimension. We do it on different examples, different features, but the same dimension. But in layer normalization, we calculate the mean and the standard deviation of the same feature, the same example, but different dimensions. After calculating the mean and the standard deviation, you can do normalization. Every output vector equals the original input vector. Wait, I found a bug here. What is this bug? The bug is that we don't need prime here. Sorry, I'll remember to remove this prime. We don't need prime here. We take the input vector and subtract m, the mean, from every dimension in the input vector. Next, divide them by the standard deviation and get x prime. The output of layer normalization. The output of layer normalization will subsequently be the input of the fully connected network. The fully connected network also has a residual architecture. So we will sum the input of the fully connected network and the output and make it residual. This new output is finally the output of a block of a transformer encoder. There is one more thing that I missed. After the fully connected network finishes the residual operation, it's not over yet. You have to take the result of the residual and do layer normalization again. We have done it once here. Here we have to do it again to get the output block of a residual network. So this is quite complicated. So the illustration we see here is actually the things we just talked about. First, you have self-attention. Actually, in the input, there's additional positional encoding. We have already said that if you only use self-attention, you have no unknown information. So you need to add positional information. In this picture, there is a special drawing of positional information. This piece, here, has multi-head attention. This is the block of self-attention. There is a special emphasis here, indicating that it's the multi-head self-attention. What does add and norm mean here? It is residual plus layer normalization. We just said that self-attention adds a residual connection. Then it uses a layer normalization. Add and norm in this picture here means residual plus layer norm. Next, we go through the feed-forward network. FC's feed-forward network. Later, do add and norm again. Do it again with residual and layer norm. That is the output of a block. Then this block will repeat n times. This complicated block will be used in a very important model, BERT. We will later discuss it. BERT is actually the encoder of the transformer. Now, your heart must be confused. Why is the encoder of the transformer designed in this way? Actually, it does not have to be designed like this. For the network architecture of this encoder, and the way it is designed now, I teach them according to the original paper. But the design of the original paper does not mean it is the best, the most optimal design. For example, there is an article called On Layer Normalization in the Transformer Architecture. The question it asks is, why layer normalization is placed there? Why we do residual first, then do layer normalization? Can layer normalization be put in the input of each block? In other words, after you do residual, you do layer normalization, then you add it up. You can see that the picture on the left is the original transformer. The picture on the right is the transformer. After changing the order, the result will be better. This means the original transformer architecture is not the most optimal design. You can always think about whether there is a better way to design. Here's another question. Why is layer norm? Why not something else? Why not batch normalization? Maybe this paper can answer your question. This paper is Power Norm. Rethinking batch normalization in transformers. It first tells you why batch normalization is not as good as layer normalization. Why in transformers batch normalization is not as good as layer normalization. Next, it talks about the power normalization it proposes. It sounds very powerful once you hear it. It can be better than layer normalization. And the performance is the same or even better.